Hello and welcome to a concept review module on data management. It's covering introductory concepts related to data and data management systems for geospatial technology. I'm Ann Johnson, Associate Director of the Geotech Center, which is a national science-funded grant to support geospatial programs. This concept will review some basic concepts about design and modeling related to data management. So we're going to look at some data types and formats and look at different types of database structures. We'll also look at the data about your data and the importance of metadata. We'll also compare the design, modeling, and data management needs for a project versus an enterprise system. At the end, we'll look at some links for more in-depth review on data management topics. So really, with geospatial data, we're looking at changing data into information. And really, to effectively do this in the digital world, we need to organize and utilize geospatial data by having data models, a structure that also includes ways to access or secure or backup or archive the data, including rules and domains for that data, its metadata, and also look at workflows and documentation related to that data. There are just many other factors to consider. So the two major types of data models are vector and raster data models. Vectors are used to define features as points, lines, and polygons depending on the scale of the map. Tins are one special way to arrange those lines and points. They're triangular irregular networks where we have edges and nodes based on an attribute, and generally these are elevation. Networks are also another special type of vector data, and they're lines with rules for connecting and direction of those lines. And if you think about them, they're mainly used for road networks or for streams and rivers. Multipatch is another special vector format where the geometry is used as a boundary representation for 3D models and objects. Rasters, on the other hand, are made up of regular cells containing one attribute. So they're little square cells, each one with a value in it for some attribute. Imagery comes into us that way. They're regular cells with multiple image layers that can be combined. One of the continuous layers that we often see are digital elevation models, or DEMs, where each of the cells contain an elevation. There are also thematic rasters, such as continuous layers that represent temperature or other attributes that cover the regions using cells. One way it is used is in hotspot analysis. So it's in a grid with a value and attribute about something. And one of the things, think about crime statistics. Where is most crime happening? What is around those cells? And you can really visualize then hotspots of criminal activity. This is just an example of a data model, and each of these are discrete features, points, lines, and polygons. So a point is just a node. A line is one-dimensional with a beginning node and a line and an end node. Polygons are two-dimensional with nodes and lines enclosing an area. So here we have points are our farmers' market points, lines are the freeways, and then the county polygons. Each of these different features includes a table with attributes about that feature, and that table also includes locational information, so it allows us to display it in a map. So vector data is, when we look at tables of data, it's non-geospatial data tables that we're often seeing. Tables contain data in rows, also called records, and in columns called fields. But note when we look at this upper table, it doesn't have any field that we could see that would have locational information or type of entity that it represents. The lower table is actually a geospatial database table, And this one contains a unique number, an ID number for each of the features. It tells us that the shape of the feature is a polygon, and embedded within that field is information on how to display or locate that polygon. And it also contains attributes. We can, using a geospatial database, relate geospatial and non-geospatial data together. And here we have our upper table, which is has locational information. It has that ID and the shape. And then we have a lower table, which doesn't have any geospatial data. But we can use one of the fields, and here it's both are called parcel underscore NU, but you'll know they're not identical. One has an uppercase, one has a lowercase u. But it doesn't matter what your field title is. It matters what kind of data is in that field. And both of these fields are numbers, so we can relate them. We can tell the table to use the designation field and relate it to the locational information with the key field. Feature relationships can have relates or joins, and it's really the type of link between the two types of tables. You can relate tables where the tables remain separate tables, or you can join the two tables together and become one table. And there are different kinds of joins and relationships, one to many, many to many. Here we have one that is many to one, where we have county codes, and then we have one that tells us where the country name for that county code is USA or Mexico. There's also many to one, caution here, where some of the joins to the first record, it may not join to other records, so you make sure you review your data. Raster data models are quite different than vector ones. Instead of having separate entities with points, lines, and polygons, it uses cells or pixels, and it's usually a continuous data surface. The cells contain one attribute about a specific type of attribution, and each of the cell's positions tell its location. So here we have a raster data set with pixels displayed with density of farm markets. And you can see by the colors, the high density is the brighter, darker orange, and the lighter colors are low density. Images come into us, and this is Landsat imagery in pixel forms or in cells. And if I zoom in to one image, and this is a Landsat 8 band 4 scene, I can begin to see those pixels, and we call it being pixelated. I can zoom in further, and each of these pixels represent a 30 by 30 meter square area on the ground, and they're given one attribute, and so you can see its digital number for that particular pixel. Imagery generally comes in with multiple layers, and your computer software can combine up to 3 of those different values that come in the cells and create a composite image. So what else is needed if you want to use this kind of data? Well, you need a database management system. So it's a structure, a DBMS, that allows you to organize your data, allows for storage, backup, retrieval, and interactions. And in a larger project, has more documentation and more standards are needed. And we'll look at a schema in a minute, but it usually needs a very detailed schema. Each data set, though, needs its own metadata and what style is used. Federal Geographic Data Committee or International Standards Organization of metadata. And it's really important when you're creating your data and building it that you document this so that the data can be used again, so that we know what coordinate system, map projection, datum, and scale, and many other things about it. You also may create a data dictionary. We saw in our little table where the NU was used. Well, that generally it's pretty easy to see that would be number, but sometimes the titles of tables are not as easy to discern. So you could use a separate table or a something within your metadata that helps you to define the definitions for all the different field names, also meaning of any codes, domains and ranges, and other information needed to accurately use that data set. So 4 components of a data management system, or a DBMS, are a modeling language. Here the schema may be a hierarchy, one to many, or a network, many to many, or relational, like we showed earlier, that shared field. This is just another graphic showing the hierarchical model, and also the network, many to many, and then our relational model with the primary key and destination key. It also needs some sort of database engine, and this is used for speed and storage and efficiency. And it will use a different database querying language, a structured querying language such as SQL, which allows you to query that data within the database. It also needs a transactional mechanism. So how do you validate things? How can you have concurrent access, or how can you have versioning, and how do you back up or archive your data? Versioning in an enterprise system can get pretty complex, and the little graphic on the right kind of shows that graphically. There's many different ways. You can have simultaneous access by multiple users, or you can have permissions set to who can view and who can edit or your data sets. You can have ways to track versioning, and you have to have ways to reconcile the versioning. So you need to remove duplicates and have a delta chamber table that can tell you which values remain and which are deleted or modified. It also helps eliminate editing conflicts. Workflow from a default version to a project version that can be edited and reposted. Multiple users can also edit and be reconciled or not retained. So there's a workflow that says when and how each of these versions will be tracked. Spatial database systems, there's several different kinds: GE Small World, Oracle Spatial, PostGIS, Esri's, ESRI's, GeoDatabase, and Carto Database. So I'm going to compare what you would need for a project versus an enterprise when you're talking about database management. Projects generally involve the limited number of users, just one or more, but really limited to a group or a department within an organization. Generally, too, they focus on one geospatial application. It may be a forester who's looking at tree types or other factors, parcels, geology, but generally the applications are similar. It's generally limited number of data sets, and really a smaller amount of data storage is needed. Maybe even able to store on a local hard drive, or could still be on a server or in the cloud. It should still have a data dictionary, tables that are helping other people understand what the attributes mean in your tables and any codes or domains. It should also still include metadata, so each of your data sets should identify what the coordinate system, its map projections, scale, datum, and really what type of data it is and what kind of uses it should be employed in. Output of any analysis can also be less formal. It may be a map or a proposed solution to a specific topic or problem presented in a story map or Google Earth. And often the option is just to share the outcomes and not really the data. An enterprise, on the other hand, involves really a centralized department that really oversees across the enterprise use of data and data analysis. It has a large number of users. They may be within the organization or may have users outside the organization or agencies, and it has multiple proposed applications, and it's extensible to other future and unanticipated applications. So once a program starts, other users may see the value of using your same data. It has a multiple user database or geodatabase or another structure with ways to look at it for oversight, securing it, providing access to who can view it, who can edit it, and creating that workflow for versioning and backups and archiving. It also has a formal and well-developed database schema with defined relationships and rules, and it should be overseen by an administrator. Oftentimes the metadata is not just FGDC or ISO compliant, but can be customized for the organization that's using it or the applications. But it should still have all of needed data. Output information may be in multiple formats, either maps in digital and paper versions, and often accessed via a web portal to the data or an interactive map. There are links to more helps. We have additional concept review models on metadata and datums. You can also look at a model course from the Geotech Center. GST 103 is on data management. There's also numerous tutorials online. This is just one, the link to just one, and it gives an example of a geodatabase. It goes through discussions of different types, and it's pretty good. Please do see the Geotech website for additional concept review modules and also the course that I mentioned, the model course on data management. Thank you. My name is Ann Johnson. If you have any issues, please do contact me.